So a lot of words, a lot of time spent. Let's finally get to some examples. It's only one page of notes, but a lot happening there. So let's try to put this together for some examples. A lot of the work that we do here is going to look very similar to the work that we did previously, but I spent a lot of time there talking about all those things because I want us to understand the foundation of how this is different from the work that we did in chapter 6. And why is that? Because when we start putting problems together and mixing them up, you need to have a good idea of what the difference is between all the different types of problems. So, soda machine is filled, or it should be soda machine is configured such that its cups are filled with an average of 21 ounces, the variance of 1 ounce squared. Again, this is a problem that should be able to be worked without a calculator. Math will work out fairly simple for you. Determine the sampling distribution of the average amount of soda dispensed for samples of size 25. Why do we have a sample size there? Remember, the sampling distribution idea says we have to have samples of the same size. So we have to specify that. Now, notice that this question starts off and says, what's the sampling distribution? You need to understand that all of your problems may not ask for this, but this is a step that needs to be done. You need to write out the sampling distribution for every problem. Why is that? Otherwise, you're probably going to have numbers running around the wrong places. You're probably going to get confused. It's just a good idea off to the side. If it doesn't ask you, go ahead and write out the sampling distribution. Write it out in symbols. It won't take you very long. It'll give you a good handle on the problem and make sure that you're using the right numbers in the right places. So I'm going to call us out to do it, and we're going to say, okay, how do I do that? How do I know what a sampling distribution is? Right? Well, we're talking about average amounts of soda dispense. So since we deal with averages, that means we're going to be looking at the distribution of X bar. You say, no, wait a minute, why do we not talk about the distribution of mu? Well, remember what a sampling distribution is. It is what is the distribution of a statistic. So I know I'm dealing with sample averages. It tells you in the problem, samples of size 25, right? So there's lots of clues here to tell us, okay, we're dealing with a bunch of X bars. And again, remember sampling distribution, weird concept, but it's this idea that I need to know what all the X bars look like. I need to know what their shape, center, and spread is. So that way, when I get an X bar, I know, is this one really weird or not? Okay, so we're going to talk about what would all the X bars look like. When it says distribution, we're thinking shape, center, spread. So I need to write out what the shape, center, and spread of X bar is. The first thing we want to talk about is what is its shape. That was the last thing we covered in the notes. And that is, again, that checklist. And I'll say it again. We're going to start off and we're going to say, is X normally distributed? If so, X bar is normally distributed. Boom, good to go. If not, we're going to check our sample size. We're going to check the skewness. See, if it's skewed, I need to bigger the sample size than 30. If it's symmetric, I need less than 30. That gets me approximate normality. Good to go. And if not, I'm going to say, well, I probably don't have a normality. And so I know when I go to my table or to Excel, my answer might be off a little bit. Okay. So I go back to the problem and I say, do I have anything that tells me that these cups being filled follows a normal distribution? And if you read through that, my answer would be no. There's nothing in there that says that. There's no picture that tells you, there's no histogram that says this is what the amounts look like. So I can't do step one. I can't, or pass through the gate one, I guess might be the way you would think about it. I got to go to gate two now and try that one. And that's where we said if my sample size is big enough, then I can say I have approximate normality. Well, what's my sample size? Well, I talked about samples of size 25. Is that greater than 30? You say, no, it's not greater than 30. You say, but 30 isn't a hard and fast rule, right? We should consider the shape of the distribution. And this is where the course gets a little bit gray. There's nothing in the problem that tells me anything about if I have symmetry or skewness. There's no picture. You don't see the word symmetry. You don't see the word normal. You don't see the word, bell curve. You don't see symmetry. You don't see skewed. You don't see anything like that. And so knowing that I did not reach that threshold of 30, I would say that X bar could be considered approximately normal if X has some symmetry. If X doesn't have symmetry, then I could not say it's approximately normal. Okay. So that's the shape. Then we got to find center and spread. Center is a simple one. the mean of the x bars is the same as the mean of the x's. That's what mu sub x bar equals mu sub x means. The shape of the x bars is the shape of the x's. The center of the x bars is the center of the x's. So the center of the x's is 21. So that means the center of the x bars is going to be 21. How did I know that was mu sub x? Because it says that the machine is configured where that the individual cups average 21. It's configured such that all the cups get 21 ounces. An average of 21 ounces, that's mu. That's mu of all the individual cups. That's mu sub x. So that's going to be the mean of all the x bars too. And the last part's the spread. The spread, the variance was 1 ounce squared. Of course, that means if I want standard deviation, I have to take the square root of that. Luckily for us, the square root of 1 is 1. But that's the standard deviation of the x's, of the individual cups. I want the standard deviation of the x bars, so I have to take that standard deviation of 1 and divide it by square root of n, which is square root of 25. 1 divided by 5 is 0.2. So I would say that x bar follows an approximate, approximate normal distribution with those parameters if x has some symmetry. Knowing that the cups only hold 22 ounces of soda, what is the probability that a sample of 25 drinks filled will have a mean amount that overflows the cup? It's a probability question. Just find the probability. So I want to know what the probability of a certain thing happening is. Probability that a sample. Okay, so probability of a sample will have a mean amount. Probability of a sample mean. Okay, so this is a probability of x bar. See how we got that? We said, just read the question. Probability that a and you sample of will have a mean, a sample mean. So there's a probability that x bar, and then it says overflows the cup. Now this one doesn't actually say probability that x bar is less than this, greater than this, in between this. It says overflows the cup. Well, now I just have to use the rest of the problem and say that the cup holds 22 ounces. So overflowing the cup is that x bar would be greater than 22. So first step, write out your probability statement. Now, we're going to work this problem the same way we worked the problems previously in chapter 6. Anytime I have a probability of a variable that has a normal or approximate normal distribution, if I can standardize that normality, then I get to a z. I can go to my z table or I can go to Excel. So how do you standardize? Subtract the mean divided by the standard deviation. I'm going to do it just like I did before. I'm going to do symbols on the left, I'm going to do numbers on the right, but the symbols here are going to be a little bit different because this is not going to be x minus mu over sigma. This is x bar. So I have to subtract the mean of the x bars. Well, the mean of the x bars is still mu, but the standard deviation of the x bars is sigma over square root of n. Then I do the same thing on the other side. The standard deviation of the x bars is that 0.2. That's why I said maybe write that sampling distribution out. Even if the problem doesn't ask you to. Alternatively, as long as you remember the formula, you could have here put 1 divided by square root 25. Would have been fine. And then we just do the math. This, because we have intentionally standardized this, again, standardization does not mean we get to go to a z distribution, but if we standardize something that's normal, we get to go to a z distribution, and then here we just get whatever the number happens to be. So probability that z is greater than 5. And we just go to Excel or our G table because it's greater than, we've got to work with the complement, and we can finish off with that probability. And now your next example, I want you to notice how the question is very, very similar, but you're going to get a different answer because when we take a word or two out, it changes the complete meaning of everything. Notice that the next question, while looking similar, doesn't say find the probability that the average drink overflows in a sample of size 25. It says what's the probability that one drink overflows? And now this is actually a problem from chapter 6. This is a problem that you could have done previously, in that we would say, now I'm looking for an individual x. When I standardize that, I would use a different standard deviation because now I'm talking about one drink, not a bunch of drinks. And then I would work through, just like I did in chapter 6, to find the probability. And then the last thing asks us to address all our assumptions and discuss the validity of your results. This is going to be a common question asked. We're always going to want to come back and do this for every problem in chapters 7 and beyond. This is a chance for you to do two things. One, we are going to check our mathematical assumptions. Two, we are going to check our sampling methodology. Okay, if there is anything in our sampling that would cause a problem, this is where we point that out. This is where we think about those biases that we introduced in chapter 1. The other thing that we're going to do is we're going to come back and check our mathematical assumptions. What that means is we are checking basically to see, did we actually have the normality we said we had when we went to the z-table? Remember at the very beginning of this problem, we said x bar is approximately normal only if we have some symmetry. Do we have some symmetry? Well, I don't know. This is a good place to talk about that. This is a good place for you to show me I didn't just look at a sample size and say, yes, it works or no, it doesn't, but I can talk about that, right? And so this is where I want us to get comfortable with expressing these ideas. There's a lot of different ways you can word this. Don't think the way I wrote it is the only one, because it's not. But I would say we have some concern for our results, right? Remember we said at the beginning, x bar is approximately normal only if x is fairly symmetric. Do we know if x is symmetric? I mean, maybe not, but the problem doesn't tell us it. I'm no expert in how soda machines work. Maybe you are, and you could talk about that, but that's not a common knowledge thing. So I'm going to say, because we don't know the shape of x and our sample size isn't overly big, we can't really be sure that we have that normality, which means we have to be a little bit concerned about our results. We went to a normal table, but we don't know if we have normality with the variable that we use to get all the numbers. Okay. Then our last example for this section. Notice this example is the same that you had in chapter 6. Height of woman is normally distributed with a mean of 64.5 inches and a standard deviation of 2.4 inches. But now we're going to be talking about some sampling distribution. So it says, what's the sampling distribution if we have samples of size 5? So again, this is where after seeing an example, you may want to pause and see if you can work through these going forward, if you can figure out what we're doing before I do it for us in the videos. I would say that x bar follows normal distribution with the same mean of 64.5 and a standard deviation of 1.07. How did I get 1.07? Because we took that standard deviation of 2.4 and we divided it by the square root of 5. Why did I not put a dot over that tilde? I mean, yeah, because we don't need to say that we have an approximate normal distribution. Why is that? Because if we know that x is normally distributed, then we know that x bar is normally distributed. In this case, we know x, the individual height of a woman, has a normal distribution, so that means x bar is a normal distribution. I don't have to look at central limit theorem. I don't care. I did my first gate passed, and so I can just say, yes, x bar has a normal distribution. Now I get to go to that normal table. I get to go to Excel and use that norm.dist function with no worries. We know we have normality because we started off with x having normality. So now the questions will work out pretty similar. Find the probability that a randomly chosen group of 5 women heights average more than 67 inches tall. So I have a couple of clues as to why this is a probability of x bar question, not a probability of x. First off, I see the word average. Now I have a group of 5, right? So a couple of different keywords there. So the key is just make sure that we write out our probability statement correctly. And then just like before, we standardize both sides, work until we get a probability z less than, then go to my table or go to Excel. Should be pretty straightforward. Once we know what we need to do, that's the hardest part of this, is identifying what type of problem we're dealing with. And so make sure you're picking up on those keywords, those key ideas. Don't focus in on the exact words of this problem. The next problem is going to have words slightly different. I couldn't create the same wording even if I tried. Pick up on the key ideas though. One idea is, what's the probability that one person, one city, one tree, one computer, one car does something? The other one's probability that the group averages something, right? Those are two different ideas. Make sure you can pick up on that, and that should set you up for success with a good probability statement, whether it's probability of x or probability of x bar. And then we're going to extend on this in the next lesson to how we handle proportions, but it's just the same concept, just a different extension. For this one here, we're between So just like before, we're going to standardize both sides. We can also find quartiles, percentiles, cutoff values for these as well. So notice this question here says, what's the third quartile? Well, now we're just going backward, just like we talked about before. A third quartile means that 75% of the values are less than that. So we need to find what's that z-score. Well, that z-score will be 0.67. And then I just have to unstandardize. I have to unstandardize the exact same way that I unstandardized before. Is if I know that a value minus mean divided by standard deviation equals my z-score, I can just plug in and solve algebraically. In this case, my standard deviation, that sigma over square root of n was that 1.07. I have to multiply that by both sides, add the mean to both sides, just work out a little algebraic equation. I can get a value just like we did before. And then, of course, familiar question, find the probability that we randomly selected a group of 5 women that have this average height. So of course that's probability that x bar equals 65.22. A lot of people from here will start working through this and say, okay, I got to standardize both sides. No, you're getting ahead of yourself because x bar, we already said, follows a normal distribution. A normal distribution is a type of continuous distribution, and continuous distributions can never have exact probabilities. So I don't have to do anything. I can just say the answer to that is 0.